In this lecture, we discuss two methods that can be used to create digital filters. I'll discuss these methods while using a low-pass filter as my example, but these methods can be used to create any type of filter. Let's suppose that we want to create a low-pass filter of length n. Since we know the general shape of the ideal filter, and we know the length of the filter we must create, we can require that the filter that we create perfectly match the ideal filter at the end points. Although we can specify the magnitude and phase of these samples, we cannot specify the magnitude and phase away from these samples. So this method will still produce ripples in the frequency response. Filters created by using this sampling method will match the ideal filter only on the samples we defined. We can reduce the size of the ripples by using a number of techniques. Perhaps the most effective method to reduce ripple size is to widen the transition band. If we allow one sample in the transition band to be unspecified, we can use a computer's aid to find a filter with a transition band that minimizes the size of the ripples. Since designing digital filters by hand with the frequency sampling method is often impractical, we typically use computer-aided design methods to create the filters we desire. The Parks-McClellan algorithm is the most popular computer-aided design method. The Parks-McClellan algorithm creates an optimal filter, where the optimal filter is designed to be the implemented filter with the least amount of total deviation from the ideal filter. The ideal filter would be defined from 0 to a passband cutoff frequency, and from a stopband starting frequency to pi. As mentioned before, the transition band is left undefined, so we can minimize the error in the passband and the stopband. The function r of omega is the real function that we would use to create our generalized linear phase filter. The programmer has the power to specify omega sub p and omega sub s, and the programmer can also specify how much error they are willing to accept in the passband and stopband. The programmer specifies the amount of acceptable error by creating an error weighting function. If we weight the error for one band of the filter very highly compared to the weight for the other bands of the filter, then we are willing to accept less error in the band with the highest weight. Typically, we specify one weight for the passband and one weight for the stopband. These weights will force the filter to not deviate from d omega, the ideal filter, more than a fixed amount. As it turns out, the error is minimized if the ripples in the passband are the same size and all the ripples in the stopband are the same size. To conclude, let's recap. To create a filter using the frequency sampling method, we use computer-aided design methods, such as the Parks-McClellan algorithm. The filter designer can specify the frequency range of the passband, the frequency range of the stopband, the error weighting of both frequency bands, and the length of the filter. If the designer wants to decrease the size of the transition band, then he must increase the filter length. If the designer wants to decrease the size of the ripples, he can either increase the size of the transition band or increase the length of the filter.